One of the things that I didn't talk about too much is that networks are also having heterogeneous properties. Okay. So, when I said networks, I said that, okay, link exists or does not exist. Okay. But many of the networks we see in nature are actually weighted. Okay. So some links are strong, some links are weak. And you know that in your friendship network, right? You have friends, but not all your friends are, friends to an equal degree, right? Some you can confess things, others you have more kind of a head nodding acquaintances and so on. So you can quantify the nature of the relation by associating a number. So you say that this is the strength of this link with this particular node. Same thing happens for biological networks. So some synapses are strong, some synapses are weak. Okay. And those of you who have worked on neural network, you know that basically it's the weights where actually the secret of the power of the neural network lies. I mean, learning is actually happening by tuning the weights. Okay. So weights are actually ultra important, and this is something which I have not dealt with at all so far. Okay. What is also interesting is that the weights can not only differ quantitatively but qualitatively. And what do I mean by qualitative? So it means that you can not only be friends with people, you can also be enemies with people, right? And you can't really characterize enmity by just increasing or decreasing the strength of the connection. You actually have to associate a plus or a minus. So a relation can be qualitatively different, not just quantitatively different. Okay. Some relations would be positive, some relationships would be negative. Okay. And in the context of the neural network, we know that some strengths would be excitatory. That is, if one neuron gets activated, it will help activate the other neurons, and some neurons are inhibitory. So if it gets activated, it would tend to suppress the activity of the other neurons. Okay. So you can have both quantitative and qualitative differences in the nature of the connections. Okay. And this is actually very important in understanding the functions of certain kinds of networks. But before getting there, the most important thing is that these weights can be adjusted rather than altering the connection topology of the network. Okay. So in neural network, for example, you can do learning by, instead of changing the connections, you can actually just alter the weights. Okay. But suppose you ask me, okay, but can we actually change the network's behavior by actually altering the connections? Or how can we make a network actually evolve over time by changing the connections? So let's first look at that. Okay. So the question that Barabashi and Albert in their very influential paper of 1999 asked was that, how do networks evolve to a particular kind of degree distribution? Okay. And the kind of degree distribution they had in mind was what are known as a power law distribution. Okay. Is this power laws familiar to anyone? Have you heard the word power law before? Okay, 1, 2, 3, 4. Okay. Maybe a few more here. Okay. So suppose you have something like this. Okay. So this relation is very often referred in the literature as a power law relation. Okay. Now, it will also be sometimes called scale free. Okay. And the reason has to do with the fact that, unlike, let's say, something like this, okay. So this is not scale free. Why not? Because if you look at inside this exponential argument, you find that there is this quantity b which has the same dimension as the variable x. Okay. So if x is, let's say, time, then b also represents time. Okay. And a famous example of this is the radioactive half-life. Okay. So I ask, okay, how much of a particular material will be remaining as it decays after a certain point of time, and you know that it follows this kind of a distribution. So this tau is this half-life or the characteristic time, it's related to the half-life of the substance. So essentially it says something about a characteristic scale. It could be a spatial scale, it could be a time scale, as in the case of half-life. Okay. By contrast, if you look at this, this is actually dimensionless. It's a constant. Okay. It's a number. Okay. So it does not represent any property of the variable. It's just some arbitrary number. Okay. And so what it says is that now you no longer have any characteristic scale in the system. Okay. Now why is that important? See, often when we have a distribution, then we tend to say, okay, we have a distribution, we have a spread in the values. Let's say the height of the people in this room. We have a spread, not everyone will be of the same height. But you can express the average height and maybe also the dispersion, and that gives a fair idea about how the heights are of the various people in this room. Okay. And so that would be characterized by, let's say, a Gaussian distribution. And as we know, Gaussian distribution has the form, well, modulo this 1 by root over 2 pi sigma square, it will have this x minus mu by sigma whole square form, right? So this has both the mean and the variance inside the distribution. Okay. Contrast this with a distribution where actually the distribution goes as p of x by x goes as x to the power minus alpha. This now has no information whatsoever about the mean and the variance in the distribution. What it means is that now the mean and the knowing the mean and the variance gives you no clue about what are the outliers in the system. For all you know, you could have people who are 100 times higher than the average height in the room, if height did follow this kind of a power law. Okay. So when financial market fluctuations are analyzed, we find that they actually do not follow Gaussian distributions, but rather follow power laws. And that's a very worrying thing, right? Because that says that, see, if it was a Gaussian distribution, life would have been so easy. So that would mean that, you will have 3 sigma variations, even if the variance be very large, you will have 6 sigma variations 99% of the time. Okay. So most of the time markets would not move beyond this range. So having something like a 10 sigma event would be, let's say, once in a millennia event. Okay. But if it follows a power law, all bets are off. You could have 10 sigma events happening every decade or maybe every 5 years. Okay. The probability is so high. Right. So having power laws means large deviations are going to become very common. Okay. Now, why did they start looking into this? That's because when they started looking into the degree distribution of some real life networks, namely the actor collaboration network, the same one that we talked about yesterday in the context of small world network. So actors are the nodes, and if they acted in the same movie, that's basically a link. They found that actually over some range, it follows. Okay, now how do you know this is a power law? Sorry, let me also explain that. Okay, so how do you know that something is a power law? Very quick, rough and ready measure. Okay. So suppose your p of x goes as e to the power minus x by b. Okay. How do I very quickly eyeball something and say this is an exponential distribution? Of course, you can try plotting it, but This could be an exponential, this could be some polynomial. Just by looking at it, it's very hard to make out. Taking log. So take log. Okay. So the moment you take log, so what you can do is you plot it in a semi-log graph paper. Okay. So the y-axis is log. Okay. And this is a normal axis. Okay. So basically that means this goes as 10 to the power 0, 10 to the power 1, 10 to the power 2, 10 to the power 3 and so on. Whereas this is going as 1, 2, 3, 4, 5, 6 and so on. Right? So this is your log of p and this is your normal x. Guess what it would look like? It's a straight line and the slope would actually give you 1 over b. Okay. So that's the easiest way to find out that you've got an exponential distribution at hand. Okay. Now, what if you have a power law? Again take log. So what do you get? Log of px now goes as minus alpha log of x. Sorry. Exactly. So you take log on both sides. So log on the x-axis, log on the y-axis, and it will show you a straight line having slope alpha, or rather minus alpha. Okay. Now, this is the physicist's way of doing things, rough and ready. Okay. Mathematicians would be horrified by this kind of a gung-ho attitude to data, and they've got good reason. So there was a time after Barabash and Albert's paper came out when everybody was finding power laws left, right and center. So the number of papers which came out with power law degree distribution in their title probably runs to probably thousands. Okay. Later people went back, analyzed it much more carefully and found that most of them are not power laws. Okay. And this has got to do with this gung-ho attitude towards power laws, because the problem, as Mark Newman famously remarked, is that suppose you have a curve like this. Okay, it's not a straight line. If you focus on a small range of it, it will look like a straight line. Okay, you take a circle and provided you look at a small part, it will always look like a straight line. And many of these power law papers actually did that. Okay, so they looked at a small part of the data, found a straight line and claimed it to be a power law. Okay. Whereas if you look at the entire range, it's actually not a straight line at all. It might be better explained by a log normal distribution, for example. Okay. So one has learned to be very careful about now calling something power law. So it's no longer, you don't just plot things like this, okay, something like this and hopefully draw a line and say it's a power law anymore. You actually have to do maximal likelihood estimators and so on. Okay. But still the human eye is a very good estimator. So as long as your data ranges over several decades, like from 10 to the power 0 to 10 to the power 5. So we say it's spanning 5 orders of magnitude and you have a pretty decent straight line from visual inspection, chances are that it will be a genuine power law. Okay. So what Barabash and Albert did was they did this something very simplistic, which is they just plotted the data on a log-log scale and claimed that look, you see the straight line portions. Okay. In the actor collaboration network, the World Wide Web, so the nodes are pages and the links are hyperlinks, the edges are hyperlinks, and the Spire's co-authorship network. So this is a database where you submit papers in particle physics and the nodes are individual authors and they are linked if they are co-authors in the same paper. Okay. And they measured the slope and they said that look, you have these numbers like 2.3, 2.1, 1.2. Whereas, in Erdos-Renyi random network, you would basically just expect to get this Poincare degree distribution. These are not exactly Poincare degree distribution. These are better described by this. So that's why they call this scale-free networks. Okay. Now, Newman has a article in Contemporary Physics called Power Laws, Pareto Distribution and Zipf's Law. Again, this is a fantastic paper. I mean, I recommend everyone to go and read this, because if you are ever going to work with power laws or Zipf's law and so on, Newman's paper is a wonderful eye-opener as to how to carefully analyze this. So don't get fooled by, the physicist's way of, just drawing a few points and then just looking at it and just, drawing a line. You have to do it very carefully, okay? And it also shows what's the connection between power law, Pareto distribution and Zipf's law, which are very similar, which are actually related things, but not exactly the same. So anyway, so this here basically I'm explaining again why, a power law essentially means that you have something which is independent of scale. Okay, so you can essentially express this in terms of so you can contrast this with distribution having a characteristic scale like exponential distribution, which has this typical time or typical space. Whereas power law distributions have this long tails. So, you have an extremely high probability of having values that are very, very large deviations from the mean, okay, and they are much larger than what you expect from variance. Now, if you look at a network with power law degree distribution, we find that typically characterized by hubs. So, what are hubs? Hubs are nodes that have extremely large number of connections compared to the average number of connections. So you could have a network whose average number of connections is 5, and hubs would be nodes which has, let's say, number of connections 1000. Okay, so you can see that several orders of magnitude larger. So this is not something you would expect from an exponential degree distribution, for example, or for that matter a Poisson degree distribution. So that's why power laws actually give rise to a completely different class of networks compared to the random networks or the scale or the small world networks and so on. So, so how do you generate networks with arbitrary degree distribution? So what you could do is something like this. So let's say you want to create a network with some degree distribution which is given to you. So I tell you, okay, I need so many nodes having one connection, so many nodes having 2 connections, having so many nodes with 3 connections and so on. So what you could do is, you could first assign these degrees randomly to your n nodes. Okay, I've already told you how many nodes should I have with degree 1, how many nodes you should have degree 2, how many nodes with degree 3 and so on. So you pick nodes at random from your set of n nodes and say all of you would have degree 1, all of you would have degree 2, all of you would have degree 3 and so on. So you create this half stubs, okay, and then what you do is start matching stubs, okay, and in this way you can actually generate networks which have any arbitrary specified degree distribution that you want. So that's one way of generating networks with arbitrary degree distribution. There are some subtleties, of course. As a student, when I was teaching this course earlier, mentioned to me, hold on a second, as I keep doing this, the number of stubs available to me is decreasing. At some point, I may end up with a situation where a node has, there's only one node remaining and it has 2 stubs. And so I'll be forced to connect the node to itself, right? Yes, you'll get problems like that, okay? So what you do is, you keep doing this over and over again, okay? So you create an entire ensemble. So there will be a few nodes which will have self links, and there could be multiple links between 2 nodes and so on. But over the ensemble, this would become very, very few in number, so you can still do your statistical calculations, okay? All right, but of course, this does not explain how would scale-free networks actually evolve in reality. This is an artificial way of just generating networks with whatever degree distribution you want. And so then Barabash and Albert found a mechanism And it turned out that they were not the first to propose this. Long before them, someone called Derek Solar Price had actually proposed this same principle. So the idea is that the network starts with a single node, and then you keep growing the network by adding more and more nodes. Each node, each new node that you connect has a fixed number of links associated with it. And what you do is you connect these connections which are dangling from these new nodes to the existing nodes. Okay. Question is, how do you do that? If you did it randomly, you'll still get a random network with a Poisson degree distribution. You won't get a scale-free degree distribution. So you do it in a particular way, that is, you connect these dangling links to nodes which are already highly connected. So you have a preferential attachment scheme. You say that the new nodes which are coming in prefer to connect to nodes which are already highly connected. Okay. So the probability is proportional to the number of degree of the existing nodes, and if you keep doing this, eventually you'll get a network whose degree distribution has this particular form. So alpha is actually 3. This actually led to some problems because you remember that Barabashi and Albert's empirical networks had exponents all over the place, 2.1, 2.3, 1 point something, whereas their generative model can only generate a single exponent, 3. So then they started playing with new additional parameters to generate networks with other exponents and so on, but then it becomes slightly less elegant, right? So as I think it was Wolfgang Pauli who said that, give me 3 parameters, I can fit an elephant. Give me 4 parameters, I can make the elephant wag its tail. So if you keep increasing parameters, of course you can do anything. But always the aim of modelers is to try to do a model which has as few free parameters as you can get away with. Okay? Because the more parameters you are, that means the more arbitrary things you can actually doing. Okay, so what is this preferential attachment scheme in general? So this is Derek Solar Price, who in 1976 wrote this paper, and it's not a wonder that physicists didn't know about this paper because it came out in Journal of the American Society for Information Science, which is read only by people in library science. Okay, but it's a model which goes beyond library science, although he framed it originally in terms of library science. Okay, so his idea was very simple. He said, why do some people get 10,000 citations and why do most of us are lucky to get 50 citations? Okay, is it that the people who get 10,000 citations are like their work is 10,000 times more valuable or 1,000 times more valuable than ours? Or for that matter, maybe people who get 1,000 citations versus people, actually no, people who get, let's say 100 citations versus people who get 10,000 citations. Is it like the people who get 10,000 citations are that much more important than people who get 100 citations? And he pointed out that it may not be anything to do with the value of the paper. And he gave a very simple illustrations. So if you have ever written a dissertation or a paper, you'll resonate with this story. So you have done a lot of work and your advisor says, okay, write it up. And you write it up and take it to the advisor. And of course, the introduction is something that is the last thing in your mind. And the advisor says, hey, where's the introduction? That's the most important thing of the paper. That's probably the first thing that the examiner or the referee would read. And so you say, but sir, that's not part of my work. And so your advisor says, go back, read the literature, write the intro. Okay. So you go back, write the intro, but that's the last thing that you want to do, right? I mean, your deadline is looming and so on. So what do? You basically look up those 3 papers that you used to first find out about this subject, and you say, okay, what are the papers they have cited? Okay. So even if you haven't read those papers, you just write up something and you start referring those papers. And you just put it in your bibliography, you show it to your advisor. Advisor probably does some grammatical corrections and that's about it. The paper goes to the conference. Okay. Now, once your paper gets published in the conference, The next student comes along in the lab and does exactly the same thing. Okay, so what happens is those papers which initially you had read, and they had cited some X papers, right? And those X papers get cited again and again and again, and nobody's actually read them. You're just taking a shortcut. Okay, and so this is like the best of all possible things for the people who are been lucky enough to figure in those references, because they're not being read, but they're being cited. So as some wag once told me, this is the dream of all biologists. They don't want anybody to read their papers because then all kinds of cats will come out of the bag. But they just want them to be cited without being read. Okay, so I'm sure this is true for most scientists, because if people actually start reading those papers, lots of worms will come out. Okay, but it's a very natural human tendency to actually avoid work by actually riding on someone else's efforts. But you hope that someone, the one who's actually using this data from actually has done the hard work. They may not have done the hard work. They may have also free-rided on someone else. So you got this, process going on where some people keep getting more and more cited and nobody has actually read their papers. How to actually track it down that, somebody is citing without reading? Any idea? There are interesting ways of doing this.
You can look at the overlap of the citations in related close papers or something. And if that overlap is unnecessarily high, then you can say that.
Okay, that probably will work, but that's a complicated way. There's a simpler way. When you copy down a reference, sometimes you make mistakes. So you make mistake in the starting page number. Instead of 376, you write 375. Or maybe 176, or maybe you got the volume number wrong, or maybe even the 3 gets dropped out at some point and you said 76, starting page number. Okay, so these errors also get copied, right? It's like mutation, right? So a mutation occurs somewhere in the system, and then the people who come down the line have no clue that this was a mistake, so they copy the erroneous information, and then somewhere down the line another mutation creeps in. Somebody, makes a mistake in the name of the journal. Let's say instead of Bulletin of American Mathematical Society, it becomes Journal of American Mathematical Society, and then that starts get copied. Okay, so now actually you can do a backtracking where you can start see where did this mutation start from.
Which stuff to catch such errors?
No, it's very easy because I have many examples where I've written a particular, where I've read this particular paper and then some paper catches my interest. Okay, this because this paper claims that this has said this. So I start searching for that paper and that paper doesn't exist. The journal doesn't exist. So then you have to work a bit hard to figure out what paper actually they meant. And you realize that they mistook the journal name, the volume number, the page number, everything they got wrong. Sometimes they even get the author name wrong. Okay, so there are lots of examples where these errors actually keep accumulating, and someone actually did this study where just as you do, like in evolutionary phylogeny, you can actually trace who is the last common ancestors by tracking these mutations, right? So you can actually do these things with journal references. So you can actually track down these mutations and see where it originated, and you can say that, okay, this paper was the one which actually started this whole error process. Okay, so you can actually see that this is really happening. It's not just Solar's Price's idea. People actually do this. Without reading papers, they tend to cite. And so this is a classic effect of rich getting richer, because the more you get cited, the higher the likelihood that you will get cited again, because the more visible you are, right? And so this turns out to be the case not only for let's say physics, but all kinds of disciplines. So there was this paper by, I think, so this is, I think, taken from whose paper? Chatterjee et al. Okay, where they essentially looked at a whole series of journals and found that citation distribution more or less all look very, very similar. So incidentally, this is fairly well known in other circles where this is known as Matthew effect. So Matthew effect refers to this phrase in the Bible, or this thing in the Bible where Matthew 25:29 says, "For to all those who have, more will be given, and they will have an abundance, but from those who have nothing, even what they have will be taken away. Okay, and Robert Merton actually had written a paper where he said that if you are a well-known scientist, you actually get disproportionate credit for your contribution. So if you write a paper with a famous scientist and you did all the donkey work and the famous scientist just put their name, guess who will be credited, who will be asked to give the talks for that work? Not you, right? And everybody would say, have you seen this guy's work? Maybe in front of you. Okay, so already famous people will start, accruing the benefits of their fame. Okay, so fame begets more fame, so to say. So this is what underlies the scale-free degree distribution. So again, I have actually a technical proof of how this 3 comes about, but I won't give you the details. You can actually work it out. This is actually fairly easy to understand, this argument of how the distribution of k to the power minus 3 actually comes about. And okay, so I will probably end in just, I'm completely over time, so I'll just end saying that, look, these hubs of a scale-free network are actually ultra important. Why? Because they give robustness to a network to random breakdowns. Why? Because these few hubs are actually responsible for connecting almost the entire network. So if you have nodes having some probability of breaking down, the chances that all the few hubs will break down is minuscule, right? Maybe there are just 3 hubs.
What does breakdown mean?
A breakdown means, let's say, component failure. So you have some probability of component failure which causes the hub to be non-operational. Okay, so let's say the probability is 0.01. Okay, now of course over a given range of time there will always be some nodes which are breaking down, but
Deleting the vertex.
You might say that, yeah. So the probability that all the few, so let's say there are 4 hubs in the system, the probability that all 4 hubs will break down is incredibly small compared to the probability of any set of 4 hubs breaking down. Okay, so the probability of random breakdown is extremely small if you have a hub, and the thing is that because the hubs essentially are carrying out the burden of actually connecting the network, even if lots of other nodes are lost, you don't feel the effect. The hubs are actually carrying the weight. But there's a downside to it. Okay, sorry. There's a downside to it. The downside is, can you guess what's the downside? What's the Achilles heel of a scale-free network?
Virus propagation.
So if you are a terrorist and you want to do a denial of service attack and you know the hubs, you don't have to attack all the nodes, you just attack those 4 hubs. That's it, the network is going to go down. Okay. So while it is robust to random failure of components, it is extremely vulnerable to targeted attacks. Okay, so that's the Achilles heel. Okay, so people have looked at the role of scale-free networks in processes like epidemic propagation. So they have done this compartmental SIR models, or in computer viruses you can do the SIS model. So from this they have come up with certain outcomes about how the network actually affects the propagation of the epidemic. And one of the important things that people measure from all this is that what is the minimum immunization coverage required to stop an epidemic. Okay, so like for example, if you have the basic reproduction number, so this basically says how the epidemic is spreading, how quickly it is spreading. So if you know the basic reproduction number, you can actually calculate what is the fraction of the population you need to vaccinate in order to stop the epidemic. So for example, COVID had a reproduction number between 2 and 3. And so if it is 3, it says that you have to vaccinate at least 66% of the population in order to stop the epidemic. Scale-free network, it turns out, has no such threshold. So even if you have vaccinated 99% of the individuals, it will, as long as you don't get all the hubs, it will still be able to find the few who are still susceptible. But the silver of hope is that if you can manage to find the hubs and vaccinate them first, you have a much more efficient way of stopping the epidemic. So this is again a very famous paper, came out in 2003, which showed that for epidemics, scale-free networks have no threshold. But then there was a reaction to all of this, and so recently there's a lot of debate as to, are actually networks really scale-free? So suppose I show you this graph. Is this really indicative of a power law? There's a huge amount of scatter, and unless you actually put in this line, I wouldn't actually say whether it's a power law or a log normal or exponential or whatever. And so this is where we come into what we were talking about before, that most of these claims of this power law networks has to do with the fact that people do very shoddy analysis in the early days. So now when you go back and reanalyze, it turns out that many of these so-called power law networks are not power law at all. And as concerns the epidemic thing, there's a brilliant article by Robert May who showed that fortunately for us, most social networks, physical contact networks along which diseases spread. So, for diseases to spread, you actually have to be present physically close to another person. So it's not like social networks which you can have thousands and thousands of acquaintances. You can only at most, contact a few people over a period which will be infectious. So most of these real life social networks on which diseases spread are actually not scale free. There's only one exception. And that one exception is the network along which sexually transmitted diseases like HIV spreads. Now, what is special about HIV? HIV has a very, very long period in which it is dormant in the individual, but the individual is infectious. So the individual has no clue that he or she has HIV, like could be a period of 10 years, and then suddenly it burst forth, right? But during this period, any person that this particular person has had relations with would actually get infected, okay? And so if you now accumulate all the contacts that this person had over the last 10 years, you would actually get hubs. Okay? So diseases which have long periods over which they lie dormant, okay, where the person is infectious but is not showing any symptoms, are of course candidates where the scale-free network having no threshold could be applied. Okay, so that's why HIV is particularly so you might say, why is HIV so disease of vital importance for public policy? A lot of effort is actually spent on HIV. One is, of course, we still don't have a surefire cure, but the other is because there is actually no threshold. Even if you have a vaccine and we vaccinate, let's say, a huge chunk of the population, HIV, given that the network it spreads on is effectively a scale-free, will not have a minimum immunization threshold. So it's very, very important that it be stopped right when we detect it at any one particular location, so that we don't have a uncontrolled spread. All right. Okay, so I think I will stop here.